Yeah, what else is that?
So yeah, make sure you look that up. If you can't figure out where to find it, just email me. I'll probably send everyone a link. But we're going to continue with related rates. So this is just talking about if we have. Did everyone get a handout?
Yeah.
I didn't.
It's also on the website. I'm not sure if we'll get to this.
Oh yeah. I don't think any of us did.
Okay, so the idea is if we know that several quantities are related, it turns out their rates are related because we can just take the relationship, which is an equation usually, and just differentiate that entire equation with respect to time. So we get a bunch of a differential equation, we get an equation with derivatives in it. And so once quantities are related, their rates are automatically related. And so we can talk about the rate of one thing if we know about the rates of change of other things. And so that leads us to the topic of related rates. By the way, how do you know it's a related rates problem? What are the key things that would be in a related rates problem? Yeah?
2 or more related quantities.
2 plus related quantities. Okay, what else?
Ask to find another change.
Well, some rates will be given. And you're asked to find the rate of someone else. Of course, it's the guy that's related. Right, so that's the big idea. And it's really important that you know when you're dealing with a certain problem, because as I mentioned on test 3, a lot of the topics on test 3 happens to be topics where the question will be word problems. And so in reading a word problem, you should be able to know what technique or what route you want to take. And so you need to know when is something supposed to be done using the exponential growth and decay forms? When is something supposed to be done via the related rates method? When is something supposed to be done via the optimization method? The different types of wordings will actually hint you what to use. And we discussed that there's a 6-step process to do any related rates problem in Calc 1. And so it's not, once you actually know that it's a related rates problem, it shouldn't be too difficult to actually get through it. We spoke about the steps, and there are 2 of them that are sort of the tricky ones, where that was the one where you needed to figure out the formula and the diagram, but the rest of it is kind of just following your nose and doing what we already know about derivatives. So I believe we did the first 3 examples, right? So what I want to do is I just want to do the next 3 examples. That should be enough examples for you guys to see how this is working. And if you haven't seen it already, and the rest you can try on your own. Maybe they might show up as bonus problems, and the homework again is a lot more practice. But the homework for this, it's not due until after the test, right? If there's a topic not required for the test, I'd rather you not waste your time going through the homework. But if you're comfortable with how your studying is going and you want a little bit of extra, you can try some of these extra problems and see how you're doing. So let's actually just jump into this. We're going to jump into equation example 4. The volume of a sphere is increasing at a rate of 5 cubic feet per second. How fast is its radius increasing when the radius is 2 feet in length? The volume of, and here it gives you a formula. The volume of a sphere of radius r is given by that formula, v equals 4/3 pi r cubed. So what's the first thing we do in a related rates problem?
Read it.
We read it, right? We need to first realize that it's a related rates problem by seeing if this is the situation we have. And 2, we need to be able to pick out the important information. What's the second thing?
Draw a diagram.
Draw a diagram. If possible or necessary. In this case, not necessary. Why?
they give you the formula.
You're given the formula. Usually when you draw a diagram is for you to describe the situation in terms of a picture, and that picture will hint to you what kind of formula you want to use. So we did that example where one was a right triangle, right? And so that kind of hints you, hey, Pythagoras' theorem is something I know about right triangles involving all the side lengths. So the point of doing the second step is really to come up with a formula. But here they gave us a formula, so we can actually just skip this step. Right? But like I said, if a step is unnecessary, you just skip over that one and go immediately to the next step. So what was the third step?
Write down the given information. Write down information that you want to find.
Okay, so we need to write down what do we know so far and what do we want. What do we know?
dVdt is volume rate.
What? The volume of the sphere is increasing at 5. Yeah, so we know the rate of change of volume. dV dt is 5. And again, remember this is a derivative, so the sign actually matters. I know it's a positive 5 because it's increasing. If they told me that the volume was decreasing, I would put a negative 5. Okay, so we need to read it very carefully to know what the situation is.
Another radius.
R equals 2.
Well, r is not equal to 2 all the time, it's changing. But what we want dr dt when r equals 2. Right, so r is not always 2. But at the point at where it is 2, we want to stop the clock there and figure out how fast is the radius changing. So we want dr dt when r equals 2. So fourth step. So what's the fourth step?
Find the formula.
Find the formula. So the fourth step was to set up the equation, right? Normally we kind of base that off of the diagram that we have here, but in this case we didn't need a diagram because they literally gave us the equation. So that's the equation that relates the radius of a sphere to the volume of the sphere. The fifth step?
Differentiate.
Differentiate. And remember here, it's implicit differentiation because time is the independent variable. So anyone that's not t, little t, we think of it as some function of time, and so we have to do it implicitly. So the derivative of v, remember this?
4 pi squared dRdt.
And so now what? What's the next step?
Plug in.
Now it's to just plug in. Plug in your knowns, solve for your unknowns. So dV dt, that's 5. 4 pi is just 4 pi. R, we know at the week here when R is 2, times dr dt. dr dt we don't know, that's in fact what we want to find. So this means 5 is equal to, this is 16 pi times dr dt, which means dr dt is going to be 5 over 16. It's in feet second. Again, I don't care about the units, but I'm just going to write it here. It's feet per second. And this makes sense. Of course, the answer is positive because if our volume is getting bigger, it means it's because the radius is getting bigger. And so the radius is increasing. So you should always, at the end of these things, you should be able to look at your answer and know whether it makes sense or not. You might not be able to tell in terms of the magnitude unless it's really like out there, but in terms of what the sign is, you should know if you made a mistake or not. R is increasing, so this makes sense. And that's related. It's always these 6 steps. And if you're given information that makes one of the steps unnecessary, just move on to the next step. Any other questions? Let's do problem 5. So I mean, you'll see in future examples, there are some practical uses of related rates, but odds are I'm going to ask you about something similar to one of the first 6. So I'll usually be describing a geometrical situation where you can just Problems 7, 8, and 9, they're pretty kind of hinting towards some more practical applications here. Let's do example 5. This one has 2 parts, but they're both dealing with a cube. So it says the side length of a cube is increasing at a rate of 2 inches per minute. When the side length is 3 inches, how fast is the surface area changing and how fast is its volume changing? So we're dealing with 2 different things here. So let's do part A. Part A, step 1.
Read it.
Step 2,
Draw a diagram.
draw a diagram. So this is a cube. So you need to draw and label a diagram. You need to label it very intuitive, based strictly on how the question is phrased. So anything that's changing, you label with a variable. Anything that's not changing, you label with a constant. So how do you label this? I don't care what variables you use, but like tell me. How you
Side length is 3 inches.
Okay.
Well, yeah.
ELBT is 2.
No, I'm just talking about labeling this. We didn't get to step 3 yet. We're not done with step 2.
So put a 3 on all sides, I guess.
That's not what we would do. Why?
It's not a constant.
Because it's not a constant. You only label constants with things that are not changing, right? Here the length of the cube is changing. So you don't want to label anything with a number. You want to label it with a variable. So what?
LW and H.
L, W, and H?
Yeah.
That will actually make things slightly more complicated here.
So X, X, and X.
Use all 3 the same variables. Okay, you don't want to make things extra complicated, right? We know it's a cube, so the length, the width, and the height are the same, right? There are other times where they might describe a box where they would say something like the length is twice the width or something like that, in which case you'd have this is X and that is 2X or whatever. But you do want to label it so that you're not given extra information. You don't want to think of L, W, and H as things that could possibly be different when we know for a fact that they're not different. So once I choose a variable here, because it's a cube, because we read the problem and realized it's a cube, we can use the same variable, right? So I would label all of those X. So 3 right now, what do we know and what do we want? What do we know?
DL is 2.
Oh, we know the side length. So we know, in terms of our labeling, dx dt, and that is 2. And again, it's increasing, so it's positive. And what we want is the rate of change. How is the surface area changing when x equals 3? Right, where here I'm using A to represent surface area. This leads us to step 4. Step 4 is what? You need to come up with an equation that relates all the variables. So right, we're definitely care about surface area here. So what's surface area?
6x squared.
How did you get that?
Because there's 6 sides, and found the area of one is 2 times width.
Right. So the surface area just means the area of the surface, so you find the area of all the faces. Right? There are 6 faces in a cube, and it turns out that the area of each face is length times width. Length times width, length times width. You do that all the time, but each face is just a square of side x. So the area here, area of area of each face is x squared, but there are 6 faces. Right? There are other times when the problem might describe something like it's an open box, and so you know there's no top, and so it would be 5x squared, but it's something that you should, it's very important to actually read and describe the situation. So we have a full cube, we have no reason to believe that any of the faces are missing. There are 6 faces, the area of each face is x squared, and so here A would be 6x squared. What do we do fifth?
Plug in.
Differentiate.
Differentiate is the next thing. Right? We have to figure out some way to get the rates of change into the mix. So what we're going to do is we're going to differentiate. Derivative of A. So we're always differentiating with respect to time, so we're going to write it in the Leibniz notation for emphasis, and this is going to be
12x dx dt.
right. So x is not t, so we apply the chain rule, it is differentiation, and so now 6.
Plug in.
Plug in. I think we can fit here. And we want dA dt, so we don't know that. That just stays.
12 times 3 times 2.
So it's 12 times the x. I know my x is 3. Times dx dt. I know my dx dt is 2.
72.
So it's 72. I think it's inches squared per minute. But just writing 72 is fine. Questions on that? Let's say we're doing B. How would things change now?
I'm a bit confused of the previous problem.
About
of
where?
Of number 5, like step 5 and to step 6. I see x and I see dx over t. I'm assuming you plug in dx over t with 2.
Yeah,
But,
dx dt is equal to 2.
Oh, when x equals 3, never mind. I see it now.
Yeah, x is 3 and
Yeah.
so x is the length of the side, dx dt is the rate at which it's changing.
Okay.
It's increasing at a length of 2.
Thank you.
So let's do part B. So it's the same situation. It's also dealing with a cube. So it's exactly the same picture. We know exactly the same thing, but we want something different. And since our want changes, all of these are going to change. What do we want in part B?
Volume.
How fast is the volume changing? So we want dV dt when x equals 3, and where V is equal to the volume. So what's the equation? X cubed. Right, because the volume of a box is length times width times height, and here each is x times x times x, we get x cubed. And so now we differentiate that, that's dV dt equals 3x squared dx dt, which leads us to the following step where we're going to plug in. And this means that dV dt is what we want to find, so that stays here. X is 3, dx dt is 2.
54.
54. And this is cubic inches per minute, but questions? Yeah.
Why are we, in general, like, having dx over dt? Why do we multiply that by the
Oh, because it's implicit differentiation. So remember, it's like that thing when you differentiated the y, you multiply by y prime for the same reason. It has to be a chain rule. Because you're thinking of x. X is not just x. X is actually some function of t. And we're differentiating with respect to t. So you differentiate x cubed, you have to derivative of the outside, multiply by a derivative of the inside. Other questions? Okay, last example, example 6. Yeah, so with related rates, your t is the independent variable. It's always going to be times the independent variable. Okay, so problem 6 says the radius of a circle is increasing at a rate of 1 meter per minute. What is the instantaneous rate of change of the area of the circle at the instant the area is 4 pi cubic meters? So we went through step 1, we read, realize it's a related rates problem. Step 2, diagram, realize that's just a circle, and we're told the radius. Set A equals the area. Step 3, write down what we know and what we want. So now the radius is increasing at a rate of 1. And we want the rate of change of area when the area is 4 pi. So step 4, we're going to figure out our equation. What is it here? Here the circle pi r squared.
Where's your 20?
Okay, 5, differentiate. dA dt 2 pi r dr dt. 6, we want to plug in. Okay, so what do we plug in?
dAdt equals 2 pi.
No, you put 4 times.
2 pi.
R is 2.
You have great to
But you already have, you don't have enough information.
We don't have enough information. We don't know what r is. What do?
You go back to the equation and you figure out what R is.
Right, so again, when you get to step 6 and you realize you don't have all the information to do something, usually the answer, the missing information you can get from the step 4. So realize here, when you want to plug in, you realize that we need to find r. Go to step 4. We know that a is equal to pi times r squared, and we are told that our a is 4 pi. So you can divide both sides by pi, you get r squared is equal to 4, so r is equal to 2. Because r is a length, it can't be negative 2, it's positive 2. And so now we can get that dA dt is 2 pi times 2 times 1. So the area is also increasing at a rate of 4 pi in meters squared per minute. Okay, so cubic meters should have been squared meters in that problem. Area is measured in squared units. And that's basically it. I mean, doing more examples. As you can see, I did all these problems. I go through exactly the same 6 steps, right? The difference is your diagram is going to be different, and that will inform what equation you're using, but everything else is kind of following your nose. So once you realize that something is a related rates problem, at least in Calc 1, it's not, in theory, a difficult problem to solve, and it shouldn't be in actuality either. Yeah, just run through those 6 steps, and you should be good. So if there are no questions, we'll stop there. That's it. So our next topic is not actually curve sketching. There's a topic that we have to cover before curve sketching. That will help us with curve sketching. It's maximum and minimum values. Where are you? Maximum and minimum values. Okay, so again, because we've painstakingly developed the theory or the concept of what a derivative is, again, this is just another application. Mostly what we're going to be doing in this section is actually defining some new vocabulary terms. So there are some terms we're going to talk about. As well as how to find them. So let's cover the concept of an absolute max first. So we're moving on to section 4.2 where we're talking about maximum and minimum values. This is one of the main uses of calculus is to find where something is large or smallest as possible or largest as possible in some region. So as I mentioned, when we're looking at, for example, parabolas, we know how to do that. We know how to find the lowest point and the highest point of a parabola. That's just using the vertex formula. But for general functions, there is no general formula. Calculus is what helps us do that. So this is what we're going to do now. So let's start with some definitions first of all. Because there are 2 categories of maximums and minimums that we'll care about. So let f of x be defined on an interval AB. We say f of x has an absolute or global maximum at the point x equals x naught if f of x naught is greater than or equal to f of x for all x in AB. So this talks about the absolute maximum. Basically, it's the largest. It's the point where you have the biggest y value on the interval. That's basically what it is. We say f of x has an absolute or global minimum at x equals x naught if x naught is less than or equal to f of x for all x in this interval. So I just defined the phrase absolute maximum and absolute minimum. These will be contrasted with two other phrases, which we call them relative maximums or local maximums. So just write that down. I'll write down the other two definitions, and then I'll illustrate with some pictures for you what the difference between the two are, so we can make sure that we understand what's written here.
What's that symbol? Where you said for all x?
Oh, this symbol here.
Yeah.
It means is a member of or an element in. So basically I'm saying for any x that's in this interval. It's set theory notation. Two more definitions. We say f of x has a local or relative maximum at x equals x naught. Okay. It's very cozy in this classroom. Okay. So we defined what an absolute maximum is. Now I'm defining a local maximum. If f of x naught is greater than or equal to f of x for all x in some small interval containing x naught. Now that's kind of vague, but we're really going to take a very intuitive look at this. In more advanced mathematics, you have to specifically define what does it mean to be a small interval around something. But here, it's going to be very intuitive when I start showing you the pictures. We say f of x has a local or relative minimum. Pretty much the same thing, except you turn the inequality around. Minimum. If f of x naught is less than or equal to f of x for all x in some small interval containing write those down. I'm going to draw some pictures to illustrate so you know what I'm talking about. But these are two very important kinds of maximums and minimums that we can find, and I'm going to tell you how we can locate them and find their values and all that stuff. That's what this section is about. But these are what they are. These are the important things that are in this section, the important things we want to find out. So let's do some illustrations. First, let me give a key so I don't have to be writing out these words all the time. This is probably going to be let's use n for absolute max, little n for absolute min. These are not like official notations or anything, I just want to not have to write it down and so on. And so I will use Lm for local max and Ln for local min. Okay. That being said, let's do some examples. So here's my interval a, b. Here is my function. It's doing its thing, whatever. But I only care about the part of the function that's on that interval. A. These are the same. Okay, so we're going to be identifying some points so you can sort of have an idea of what I'm talking about. Let me just fix this in. Okay, so let's focus on this picture for a while. Can you tell me where all the absolute maximums will be? Yeah?
There's only one. It's the second highest one. It's the highest one.
Right. So this point here, that is your absolute maximum. Right? It is the point that is larger, has the largest y value of all points on the interval. Okay, so that's where an absolute maximum is. Can you tell me where an absolute minimum is?
The lowest variable.
The lowest one. Alright, so this guy here is going to be the absolute minimum of this function. Can you tell me where all the local maximums and minimums are?
The first small is a low.
This one here is a local minimum, right? So he's not the smallest guy in general, but if you look on some little neighborhood containing that guy, just a small interval around him, he's the lowest point in that region, right? Similarly here, this guy here this guy is going to be a local maximum. He's not the biggest in general, but he, in that region, if you just look at a little bit of space around him, he's the largest guy in that region. If you look at this guy, it turns out that this is also, it's also a local minimum, right? Because it's also true that if I zoom in, he's going to be the smallest guy in that neighborhood, right? So you can be both an absolute max and an absolute min or whatever, but it fulfills the definition. So this here is also a local maximum. This here would be a local minimum, and those would be our definitions.
What about after actual points? You don't include those?
In this case, they're not anything, but the endpoints are actually important when you mention that, but I'll give another illustration, I guess. It would apply here as well, but let's do something like this. That's your A, that's your B. Okay, but in this case, the endpoints don't really matter to us. What about this guy? Is there an absolute max?
Yeah.
It's crazy. The guy's sitting right here. Absolute minimum is what? Notice that there's no absolute minimum, right? Because there is no point on this graph that's smaller than every other point on that interval, because the points keep going down. Any point you tell me, there's going to be a smaller point. So there's actually no absolute minimum here. What about this one?
Okay.
Here there's no absolute maximum, but there is an absolute minimum, right? Like these guys are on the same, at A and B, these guys are smaller than everyone close to them. So this guy here would be a local, absolute minimum. Similar reason here, if you're at an endpoint, you can be both. So this here is your absolute maximum, this here is your absolute minimum, this here is a local maximum, this is also a local minimum. And that's not anything. I mean, you could make it so that the endpoints is always give you something, where you just only take a half open number, but yeah.
Why is the point at A in that one something and point A in the first one wasn't? Like the one at the bottom. Yeah, why is the point up there a maximum? Like, and then why didn't we give anything to the point A?
Because this point here, it's in the function, it's on the graph, and it's literally, its y value is bigger than every other point.
But then wouldn't that one be like the local maximum?
This one here,
Yeah.
you could think of it as a local maximum, yeah. But we could think of it as a local maximum. Usually we won't. Because there's going to be a definition I'm going to give you later that kind of gets a little bit tricky. But the endpoints really matter if they're like the biggest or the smallest. We'd want to know them. So, yeah, so that's, are we kind of getting the idea? One is talking about in general who's the biggest or smallest, whereas locally who's biggest or smallest. Yeah.
So the endpoints can only be the absolute max or min. They can't be local.
They can be local. It sort of depends on the definitions you want to hold yourself by. There will be some books where they said you have to be able to be on either side. You have to be able to open up. You know, so there have to be like something to the left and to the right of the point. But it depends. Like by our definition, we're not. really considering that, but some definitions consider that. But the main thing is to know that one is talking about, like, in general, on this entire interval, who's the biggest, who's the smallest. Then those guys, you call them the absolute max and min. Whereas on the other one, it more looks at the details. It zooms in on each point and says, okay, in this region, are you big or small? Yeah.
So couldn't you also consider A and B local maximum or local minimums for the third graph?
You could, if you're taking that definition. If you take the definition that a local max or min can be an endpoint, then yes. But I'm sort of defining it so that you have to have an open interval around it. So there's like a neighborhood, right? And that's because I'm going to tell you about something called the first derivative test, where it kind of falls nicely in line with that. But there might be some people that don't do that. Okay, so that's the main idea behind it too. So what do I want to tell you next? Do you want to give me the closed interval method now, or should I do that later? There's something called the extreme value theorem. It's very important, but I don't think I'm going to tell you about that. It won't be important for you guys. Here's something that is important, something that you will use. Some important theorems. There's something called the extreme value theorem. Right? Mean value theorem is also super important. Like super important. There's something called the fundamental theorem of calculus, and it uses the mean value theorem to figure it out. So it's actually a super important thing. So there's something like the extreme value theorem. Basically it says if f is continuous on AB, then it is guaranteed to have an absolute max and min on AB. So you recall that there were some examples where I said, oh, there was no absolute minimum. That was because it wasn't continuous. Right? Turns out if your function is continuous on a closed interval, it's guaranteed to have a max and a min in the absolute sense on that interval. So that's the extreme value theorem. Not going to use that too much. Another one is called Fermat's theorem. And this one is going to be important. It's going to be something we use all the time. So let's say f has a local max min at x naught, and f prime exists at x naught. Then you would be able to say that f prime of that point, does anyone know what it has to be?
Isn't it 0?
Turns out it has to be 0. So if you know there's a maximum or minimum at a point and the derivative exists there, the derivative has to be 0. So we're going to actually use that in a couple of instances to figure out where there's a max or a min at some point. So you should know that the converse is not true. i.e., if f prime equals 0 somewhere, it does not mean it has a max or a min there. So it kind of works in one direction. If you know there's a max or a min, then it's guaranteed that the derivative is 0. But if you know the derivative is 0, it doesn't guarantee that it's a max or a min. It's kind of weird. The converse isn't true, but it's a very useful theorem anyway. right? A counterexample here. If you look at y equals x cubed at x equals 0, right? The derivative of y equals x cubed is 3x squared. At x equals 0, the derivative is 0, but that's neither a max or a min, right? Because x cubed looks like this. This point here at 0 is not a max or a min. So just because your derivative is 0 doesn't mean there's a max or a min, but if you know there's a max or a min and you're locating it, you can check for the derivative is 0. It only works in one direction. Okay, but it's a very important theorem. It's going to be a very important point to consider where our derivatives hit 0. Because it's possible for them to be a maximum or a minimum, but we need to check something extra. Okay. So if you know there's a point where your derivative is 0, it's possible for it to be a maximum or a minimum. You need to do some extra checks, which is going to be some other tests that we're going to do. We're going to do the first derivative test and the second derivative test. But first, let's... Oh, I can... So that's an important fact. Another important fact is note f prime does not have to exist to obtain a max or min. Can anyone give me an example? We actually did an example of this before. Can you give me a function where you know it has a minimum at a certain point where the derivative doesn't exist there?
Oh, x squared, absolute value of x squared, I think.
Well, absolute value of x squared is actually just x squared. That would be no different. But absolute value of x is such a function, right? So that was the guy that was the v, that was the sharp corner. It turns out that this here is a minimum. It's a local minimum and an absolute minimum, but the derivative doesn't exist there. So it turns out that when the derivative doesn't exist, you can also have maximums and minimums. And where the derivative is 0, you might have maximums and minimums. So these are two important points for us. Points where the derivative does not exist and points where the derivative gives you 0 are two important cases that we need to be careful of. And that leads us to another definition. Yeah, there are a lot of important theorems they taught us, but this class we don't need to know them. There's the mean value theorem, intermediate value theorem. We're not going to use any of those. So this leads us to the definition. So we're going to define what's called a critical number. It's critical. We have to find this. It's called a critical number if f prime at that number is 0 or undefined. Right? The 2 points where we know that maximums or minimums can exist. Call these a critical number. The point comma x f of x naught is called a critical point. So it turns out we know that if the derivative does not exist, it can have a maximum or minimum. So that a point where the derivative is undefined is going to be an important point for us to find, because there might be a maximum or minimum there. And we know from Fermat's last theorem, if there's a maximum or minimum, the derivative will be 0 if it exists. So in the case that it does not exist, we have this. But in the case that it does exist, we need to find all points where the derivative is 0. That will help us to find the maximums and minimums. So it turns out that maximums and minimums only occur at critical points. And that's the term. That's actually the technical term for it. It's called a critical point. Okay. I think that's all the terminology we need. So here's a method. To find absolute maximums and minimums. It's called the closed interval method. Can I fit it there? So f of x is continuous on AB. 1. Find all critical points of f. 2. Evaluate f at the endpoints. i.e. find f of A and f of B. 3. Compare all the y values in the above 2 steps. The largest is going to be the absolute maximum. The smallest is the absolute minimum. That's going to be it. So critical points will help us define if there are any local ones that are also absolute. And evaluating the endpoints is just checking to see whether at the endpoints it's the biggest or smallest in a region. And we kind of compare them to make a conclusion. I think we try time for one example. What happened?
What?
Someone said something. It's tons of time. I let you guys go 15 minutes early last time. No one even told me. No one was like, Javon, our class isn't over yet. No, you all just fucked out.
Oh my god.
What's up? It's a very short example. I mean, the method itself isn't that long anyway. So on the third test, there's going to be a problem similar to this as well. It's going to give you a function, give you an interval, and says, find the absolute maximum min on this interval. And so, that's it. There's no other way I'm going to phrase it. It's literally going to be that way. And so, step 1 is to find the critical points. So you need to find f prime, set f prime equals 0 or undefined. In this case, it's a polynomial, so f prime is definitely defined. So f prime is equal to 2x. Set f prime equals 0 or undefined. And we get that 2x is equal to 0. So x equal to 0 is the only critical point. Because 2x is always defined. 2, you're going to check the endpoints. So I'm going to find f of minus 1, which is minus 1 squared. I'm going to find f of 2, which is 2 squared. And 3. F of 0 is 0 squared. And so now you compare. Of all these 3 values, who's the biggest guy? 4. So you say f of 2 equals 4 is the absolute max. Who's the smallest guy? F of 0 equals 0 is the absolute mean. And that's it. So we'll do a couple more examples, talk about the first and second derivative tests after our, well, that would be Friday when we do that, because our test is on Tuesday. And we'll stop there.